Okay, welcome back. In our parade of dead guys who have gas laws named after them, next up is Charles, and Mr. Charles had his own law called Charles's Law, and here's the setup for Charles's Law. I have a gas in a container. There's my gas in the container, gas in a balloon. It has a certain volume, which I'm going to abbreviate V, right? It has a certain size because the gas takes up a certain amount of space. The temperature of the gas in the container, there's a certain temperature and we can measure it. So we can put numbers on the volume and we can put numbers on the temperature, which I'm going to abbreviate with a T. And what Charles's Law says is if I make the gas inside of the container hotter, the balloon will get bigger. That's probably not a big surprise to you. And vice versa. If I make the temperature of the gas in the balloon go down, then the balloon will shrink. Charles's Law says a little bit more than that as well. Basically what Charles's Law says is if I double the temperature in units of Kelvin, then the volume will also double. And if I cut the temperature down by half in units of Kelvin, then the volume will also get cut in half. And this is the equation for Charles's Law. You can see the V's, they stand for volume, the T's, they stand for temperature in Kelvin, and the 1's and the 2's stand for at the beginning of the experiment and at the end of the experiment. Charles's Law is a little bit different than Boyle's Law. It says that the volume at the beginning of the experiment divided by the temperature at the beginning is going to equal the volume of the container at the end of the experiment divided by the temperature of the gas in the container at the end of the experiment as well. And there's an assumption here, and the assumption is that we are not messing with the pressure. We're not letting any gas leak into or out of the container either. This is a video that is pretty horrible, so I'm not going to show it to you, but basically the guy in the video, he has a balloon and then he pours a liquid that's extremely cold onto the balloon, and the balloon kind of shrivels up because if you make the gas colder, it'll shrink. It'll go to that, and then basically he takes his shriveled up balloon and he breathes hot air onto it and the balloon kind of swells back up again. Here is a sample Charles's Law question. You have a balloon with a volume of 3 liters, so here's our balloon. That's a horrible balloon, but you're going to have to live with it. Temperature is 23 degrees Celsius, so the temperature of the gas in the balloon is 23 degrees Celsius. You change the temperature of the balloon to 37 degrees Celsius. What's the new volume of the balloon? And remember, Charles's Law is V1 divided by T1 is equal to V2 divided by T2. You can pause the video and work through this if you want. I am going to unpause. I'm going to pretend that I'm unpausing. There is a kind of a trick in this question, and that is this. The temperatures that they give you in the question are in degrees Celsius, and remember, when you do these kinds of calculations, you have to convert to Kelvin. So we have to convert. We should not put 23 degrees Celsius in the bottom there. We have to convert to Kelvin, and the way that you do that is you add 273, so that's going to be 296 Kelvin for our T1. So our V1 is 3 liters, right? That's going to go there. So 3.0 liters divided by 296 Kelvin, that's T1, is equal to, we don't know what the new volume of the balloon is. We want to know what it is. We have to convert this to Kelvin, so we're going to add 273 to this, and if we do that, we're going to end up with 310 Kelvin. And so here is our setup to figure out what the new volume is. So we're going to have to do 296 Kelvin. We're going to have to cross multiply 296 Kelvin times V2 is equal to 3 liters times 310 Kelvin. We want to get this V2 alone, so we have to divide the left side by 296 Kelvin. But to keep the equation correct and being equal, we have to divide the other side by 296 Kelvin as well. On the left side, the 296's reduce away to 1. The kelvins cancel. On the right side, the kelvins also cancel. So if we simplify, it's going to be V2, that's coming from here, is equal to 3 liters times 310, that's coming from here, divided by 296. The only unit that we have left over is liters, and the question wants to know the volume, so that seems to be correct because liters is a measure of volume. We're going to do 3 times 310, that's 930 divided by 296. And and V2 will equal about 3.14 liters. And this is our answer. And again, we can conduct a sanity test. We can basically say, look, the volume of the balloon started out at 3 liters, and the temperature was a certain temperature. The temperature got bigger, it went from 23 to 37, so the balloon better get bigger according to Charles's law. We heated up the balloon, it better get bigger. So whatever our number is, it better be bigger than 3 liters. And is this bigger than 3 liters? Yes, it is. So at least by that measurement, we did not go insane, and we may have done the question, we may have answered the question correctly. I can tell you that, again, I say this a lot, but I'm not paying attention to the significant digit rounding rules. I'm just concerned that you can do the calculations correctly. I just don't care about the rounding rules for this class. Okay, that is it for Charles's law. Next video will be using an equation that is not named after a dead guy. Alright, see you later. Bye-bye.
Well, I tried to make it Sunday, but I got so damn depressed that I set my sights on Monday, and I